that'll work. So what's the last thing in our notes? That's the whole discussion of the potential and the quadrupole tensor. So I'm gonna start with that and formulate one more homework problem for next week. So that'll be the last assignment anyway, so we may just add to it and turn it in the following Monday. We'll see. We'll talk about that then. But, so here's what we're looking at, quadrupole tensor. And here's what I'll do. Qij integral dm. I'll leave the primes off. 3xi xj minus r squared delta ij. And then so we're integrating over the body. And this is a 3x3 matrix. And if you have enough symmetry, so all right, if symmetric, the tensor is symmetric, so if we have symmetry, then we know we just have those diagonals. So that's the one we're dealing with. We only have the diagonals. And we've done a couple of these now. I'm just going to write example. We had the ring. So here's x1, 2, and 3. We had a ring of mass m and radius r. So I did that one in class last time. I'll just write ring m r. And so you got that one to refer to. So, and you know, we had argued based on the symmetry here that these two would be the same and the third one would be different and the sum of them adds up to 0. So for the homework, let's do the disk. All right, x1, x2, x3. I'll shade this thing in like so. And we'll say we've got the disk. So that's the one we want to get the quadrupole tensor for. And it'll be very, analogous to these. These two will be equal. The third one will, sum of all three will be 0. These two will be equal. So you're only going to have to do one integral. And as far as this dm goes, your dm will be the total mass per area. D area. What's the area element if we're using plane polar coordinates? Anybody? All right, dA here. dA for area, but m pi r squared. In fact, since I'm doing it this way, let's go ahead and write rho. And we've got a density here times d area, and that density is mass over pi r squared is the surface density, and then we've got r dr d phi. Okay. So knowing that and these definitions using plane polar coordinates, I'll just write using plane polar coordinates. You shouldn't have any problems. You see the structure of it. Now the third example we're going to save for next semester. Okay? But this is the one we're really after. And that would be, so this was the disk. The third example would be the oblate spheroid, the ellipsoid, x1, x2, x3. Oblate spheroid. And the idea is it's a bit mashed down in x3 direction, but the 1 and 2 components will be the same as well. So it's actually going to share this property, and these two will be the same, that one will be different. The reason we're gonna do it next semester, we need a little more integration technique to do this one systematically. But you know, it's in a sequence of these three, and all three of them actually show the essential properties that we were making use of. All-blade spheroid, and you know, we're always getting the corrections to the 1/r potential. What's going on right here? So all-blade spheroid all right here next semester. So then when we're doing rigid body motion, it's a little reminder that we gotta make this one up too. Right? We'll be integrating over bodies, three-dimensional bodies, so next semester. So, but all of these were giving us the corrections to the point mass potential. So I'm gonna go ahead and do the kind of the standard way of showing the 1/r² field, 1/r, the spherical mass distribution for 1/r² gives you the point mass property. That's very important, so I'm gonna belabor it a little more. And what I'm going to do is go back to Physics 4B. This is where you guys probably learned this, where we did Gauss's law. Anybody remember Gauss's law in Physics 4? Gauss's law, the flux integral.
Oh, that. Yeah, there were some interesting ways you could use it.
With symmetries, exactly. So what I'm gonna do is remind you of that, and then because gravity is 1/r², we're gonna inherit the Gauss's law results. And that's not gonna be enough. We're eventually gonna prove them, do the full mathematical proof, but this is a good way to make contact with things you guys have seen before. And again, it's because gravity is 1/r², and that was actually discovered before electromagnetism. And the lore is that Newton held off publishing some of his results because he couldn't prove what we're working on right now. Okay? He used it, made sense, but he couldn't prove it. Okay. So we're going to go back to electricity and magnetism, just to make contact with that. And you know, we're looking, first of all, Coulomb's law. You've got your 2-point charges, Q1, Q2, 2, separated by R. And you guys remember Coulomb's law? The forces Q1, Q2, 4 pi epsilon naught R². Magnitude of the force. You guys remember that one? I hope so. Yeah. Okay. And then the corresponding field of a charge, Q 4 pi epsilon naught, 1/r². And if you want the vector there, then you can put an r hat or a unit vector like that if you want the vector property. So then we have electric flux and Gauss's law. Electric flux and Gauss. And there the idea is that if you have some charge distribution, I'll just write Q here. In fact, I'll make my picture a little bigger. Here's what I'll do, right? We've got some enclosed charge. So Q enclosed, and it's enclosed in some surface or hypothetical surface. And the surface has a surface normal, which I'm going to call n hat. It's always pointing away. It's normal to the surface there. Right? It's always pointing away. Then the electric flux is the integral E dot n hat d surface over the boundary of the volume, so this is just the boundary, which is the surface bounding that volume. So this is the volume V, okay. Remember the right side of this? It's just the enclosed charge divided by epsilon naught. That was and of course these integrals are technically very, very difficult to do, but when you have enough symmetry, you just can infer what they are. And so the example on this one, kind of to make your point, is point charge at the origin. So point charge Q, the origin, and when you have that, you argue the following. Point charge at the origin, we surrounded by an idealized sphere, Gaussian surface. Right, it's all coming back to you guys, right? So surrounded by that sphere. And then, if you didn't know the field, you didn't know the field law over there, you'd argue by symmetry, it has to be pointing directly away or towards. That would be the symmetry of the situation that tells you that. And then the left side of this integral would be this unknown field. It's parallel to the n hat, so that dot product gives you the entire component of E, and dA would be integrating over the surface of that sphere, radius r, so you'd say 4 pi r squared. That would be Q enclosed over epsilon naught, and then you would draw this conclusion that E is equal to Q 4 pi epsilon naught r squared. So that's a consistency check. Okay, you guys have done this in electricity magnetism. And then what you do is you apply it to other interesting geometries, like cylindrical geometries and things like that. Good. So what if we want to translate this whole schema to gravity? I should have left a little more room on the board, but gravity is a 1 over r squared force. So you guys have a little more room than I do, but I'm just going to go ahead and translate what I have on the board to gravity. And gravity, we say F is equal to G M1, M2 over R squared. And then instead of the force, if I want to just take the field, okay, so that's going to be analogous to going from F to E. If I want to go to the field, I'll do the vector as well. It's going to be minus G M over r squared. And then since I'm doing that vector, I'll have the r over r. And the minus sign I have because the field is attractive. That would correspond to, over here I could have a minus charge. Right? So can I infer the form of Gauss's law now? So I want the gravity version of this thing. See if we can pull that off. So the integral on the surface bounding this volume, we want to have G dot n hat E area so we're over here I have Q over 4 pi epsilon naught. Here I have G, right? Lowercase g. So what's my substitution on the right side here? Let's have a quick look at that, okay? So we've got Q over 4 pi epsilon naught. We're going to substitute that, I'll do an arrow, just substitute that. For minus mg, minus m capital G. Or that's what, those are what are the equivalent thing there. So it goes in there. So we should end up with minus 4 pi g, and then instead of q enclosed, we'll write m enclosed. Should I do a capital M enclosed? So that's the translation of Gauss's law to gravity. Let's go ahead and apply it now. This is a little smaller, you guys can make that bigger if you go, so it's an important step. So we'll now apply it. So the application is, application, we're gonna have, let M be spherically symmetric. So somewhere here around the origin, we've got a spherically symmetric mass distribution. It could be in layers, right? You essentially just have to have rho equals rho of r if you're using spherical polar coordinates. Okay. Then you do the same thing before. You have out here at R, your Gaussian surface, and you're asking, what is the field like that is due to this spherically symmetric mass distribution? And again, the argument is the field, the G, has to be radially inward or outward. And the way these symmetry arguments work is, what you do is, suppose it were not radially in and outward, that would mean that at this point it could have a component, right? It could have a component that is not radially in and outward. And if it had such a component, then because this is just a sphere, you could turn the sphere and you could make that component move, which is a contradictory, right? Because you just got that sphere, and no matter how you turn or manipulate the sphere, it's still just a sphere. So the symmetry argument tells us that we have no component except for a radially outward component, and that can only depend on the distance. Okay? So that's why I draw it like this here. And now we can apply Gauss's law, and we have, so now we're going to apply this integral law here. So now we'll just say G times, same argument as before, 4 pi r squared is equal to minus 4 pi G M enclosed. That's a subscript, so we'll put that here, BNCL for enclosed. Now I have to say something about the minus sign. The minus sign comes because we have an attractive force, so this integral, so this arrow is pointing in, and the surface normal is pointing out, and the dot product of opposite vectors has a minus sign. That's where that minus sign comes from in the formal calculation there. So actually, you have a minus sign on both sides because of the dot product. And what's left here, when all is said and done, is that the field G is just minus 4, well, actually the 4 pi's cancel. So the field G and its magnitude is simply G M enclosed over R squared, which is just the form of point mass. Okay, so that's that argument from Gauss's law applied to gravity. Okay, so now you could ask, can you prove Gauss's law? Does anybody remember the proof of this statement here? We may save that for later. It uses Gauss's integral theorem. It's actually an integral proof in itself. An interesting proof in itself. In this class, we'd like to prove everything. Ideally, we get it from scratch. Okay. But yeah, so that is, this is the level of proof as if you accept Gauss's integral, Gauss's law in electrostatics, right? So you have it here as well. There's a famous application of this that I'll also do now. Actually, to wrap up this discussion, so go ahead and erase this. Look at a gravitating sphere like Earth, except it's not hot inside, and you have a tunnel all the way through to the other side. What happens if you jump in the hole? You guys ever heard that thought experiment?
You'd fall, you'd reach the center, you'd keep falling back up towards the other surface, you wouldn't quite get there, you'd basically just have an oscillating fall about the center.
Also, you'd get an oscillation about the center. In fact, you'd get a harmonic oscillation about the center. So that's what we're going to look at. Now, fortunately or unfortunately, we have a liquid core, solid core, etc. Right? There's too much going on in there. But if this were just a nice gravitating body with no other properties, then you'd jump in one end, you'd go to the other side, then you could take a little hop, jump in, go to the other side, show up on the other side for a couple seconds, maybe do a flip in the middle to orient yourself, and then you'd be back again that way. So Gauss's law is going to show us why that's happening here. And so yeah, you actually want to do this example to see the application of this. Sometimes they'll even discuss this in electricity and magnetism classes, right? Because it's analogous. But good, so I'm going to erase this and make some room for that. Because we take just literally what this law here says and close, I'll write it out bigger. So you're going to have G vector dot n hat integral d area is equal to minus 4 pi G mass enclosed. And we go ahead and consider our sphere here, and we can be standing up here on top. So it has a radius capital R, but what we're going to ask is, what is the field if we take, that's kind of off center, it's supposed to be a concentric sphere inside, okay? So, you know, my radius R could be outside, but I could do this one that's inside. We'll do this evaluation, see if I can draw a better picture here. There you go. So yeah, what's going on at this point here? So again, the symmetry argument holds. You can only have, with this spherical symmetry, you can only have a field pointing in or out. And so that argument is very important to grasp. And like I said, you do it by contradiction. And then the left side of this here is now going to be G. And we're going to pick, again, because the G is in and the n hat is out, that's where we pick up that minus sign for g dot n hat. So we get minus g, and then we have 4 pi radius squared. So it looks exactly the same as it did before. Okay. On the right side, minus 4 pi g, but here's the question, how much mass is enclosed? We've got a total mass m for this body here, right? Total mass m, complete radius r. But how much mass is enclosed in this smaller sphere? You could say density times volume of the sphere if you want. So the density is total mass over 4/3 pi radius cubed. And the volume is 4/3 pi lowercase radius cubed. Okay, so that's the way to do that, and you know you'll get these nice cancellations. Your 4/3 pi is gone. So what we're left with is minus 4 pi g total mass lowercase r cubed over uppercase r cubed. And I can now say, what is g equal to? G, that gravitational acceleration. 4 pi's cancel. And the minus signs cancel as well, so that's g m r over r cubed. Oh, sorry, epsilon. See, I got rid of 2 of these powers here. I've got the whole thing here. And by the way, when little r reaches big R, then I've got 1 over big R squared, right, which is the field strength of the surface, so we're good there. So what do you guys see about this? Let's write it this way. We've got gm over r cubed parentheses times r. It's linear. It's linear in r, and we know it's attractive. So since we know it's attractive, we can say G is equal to minus Gm over r cubed r, and then we could have this r over r like that. Direction. But the point is, it's a linear law harmonic oscillations. That's simple. Okay. We've talked about that before. Once we have a linear law in our dynamic variable, then we can just rename the letters and talk about harmonic oscillations and talk about frequencies and so forth. So let's even do that. So I'll just write this as linear law. This is linear. So what we have here is here's write this clearly. We have a linear restoring force. That's the way to look at it. Linear restoring force. So if we put a mass there, we have m, and this is the acceleration, right? So we have ma would be equal to, in fact, we can do this, mr double dot would be equal to minus gm over r cubed times m. In fact, we'd have to put the mass here. mm times r. However, because now this r is allowed to go positive and negative, I'm going to rename it to x so that we have the times x. And since gm over r squared is a force, again, now r squared is a force, so that's a force per length, not length, that's a force, so that's a good force law. So what's our frequency of oscillations? And our period of oscillations? Omega squared is going to be this divided GM over OP. So actually, what we really want to hold on to, harmonic oscillations. We could name this thing K. Right? Good, so that is where that comes from. You've heard about it before. And let's see what else. Gauss's law. Gauss's rule there. Put that one on. So yeah, this is an important, in fact, you know what, let me, I got this result, let me go back over this calculation, it'll be a little more formal for you. Okay, yeah. Just to make sure they'll just kind of skip the steps. So let's do this. We'll go back to this formulation. Maybe skip fewer steps. So let's focus on the right side. So I'll just rewrite the left side. We've got the boundary of a volume, the field times the surface normal. So this is what's happening at the surface of that bounded volume. Okay, so you know, here's a volume, total mass M. Now, this is the surface. So I'm using that symbol del V for the second, right, the boundary of the volume. And then we've got that surface normal everywhere in hat. So yeah, let's make sure we didn't leave this off the plate. Okay. Then what we have is minus 4 pi g, which is natural constant. How do we express the mass that's enclosed? I kind of skipped a step for you guys, just assuming this. The mass that's enclosed is actually the density, right? D3R, if you want to call it, just that's the volume element times the density, and that would be over the entire body. So that's what I was doing. I skipped a step. This side, of course, we just dealt with. We had the symmetry G 4 pi r squared. We're done. This side, we were actually integrating over a density, right, and a volume element. But because I had the spherical symmetry, so just to remind you, what I did was I said, in this case, the density is just the mass over 4/3 pi radius cubed, total mass over total volume. Okay. So that's what I was doing there. And then the D3 volume, since it was uniform mass, I just said we multiplied by the full volume, okay? But you know, if you're doing this formally, then you want to have all these pieces here. So I skipped a couple of steps, right? So you can refer back to what I did. And that would be the thing. So that's the expression for the enclosed mass in a certain volume. And this is the expression for the flux through the boundary of that volume. Good. I should have done that before, but does that make sense to you guys? Yeah. Okay, so I'm just going to use the rest of the hour to start talk about where we're headed. So we now have some properties of extended bodies, really important ones, but this property was that it reduces to a point mass property. But the quadrupole expansion showed us that we can, we can actually get the features of, if we had a potato-shaped planet, right? If we're far away from it, it would just be like a point mass. If we get close to it, we'd have to bring in those other features, mainly the mass distribution. So the next step is to talk about mechanics of systems of many particles. Up until now, we're always just talking about one particle that's orbiting, something else, affected by something else. So the whole next section, and then we'll be into that in next semester too, will be mechanics of what's called point systems, or systems of point particles. And then, of course, the many variable calculus comes into play as well. Sometime when we're doing integral theorems again, we'll do the Gauss's integral theorem for Gauss's law. But I don't want to belabor it right now. Okay, so here's what we're doing next. This is called point mechanics, or systems of point particles. The idea is that you can build up the whole mechanics. You started with a single point mass, and you have some systems of point masses. And then if you take this system of point masses and say they're all rigidly locked into place, then it's a rigid body. If they can move a little with respect to each other, it's elastic, and so forth. So that's the progression between systems of point particles and Newton's law holds. That's kind of where we're at. So instead of just having one mass, well, we already had two masses when we talked about the two-body problem, briefly. So here's what we have now. We have m sub I located at vector r sub I, but we've got a whole bunch of them. And I'll just give one vector for one of them for the moment. Okay. So what's the law of force on this ith particle? Well, it's Newton's law, m sub I, r sub I, second derivative. And you say that's the force on the ith particle. But that force on that ith particle is due to all the other particles, plus maybe some that aren't even in the picture. So what we do is we become a little more specific here for m sub I, r sub I, second derivative, is equal to, I'm going to write here, f sub I external, and I'll write here f sub I j equals 1 to n. So now what I'm saying is, it's just Newton's law as before, but these are all the forces. In fact, we can then write j is not equal to I. It's not acting on itself, but these are all the forces due to all these other particles acting on this one. What about this external one? It's just like in this room. We get a collection of particles connected by springs, right? But then, in addition to being connected by springs to each other, they're all subject to outside gravity. Okay? So the external force could just be the gravitational force in the room, and then this would be all the individual forces acting between those. So this is a useful way to break things up. We can actually get some interesting results off of that pretty quickly. So yeah, I'll just write external force acting on all of the particles these are the forces between the particles themselves. So you know, we get one interesting application on this. So these forces acting between those particles, and all of these forces are subject to Newton's 3 laws. Yeah.
So we're looking at this in the case where the particles aren't free to just move, however?
Actually, they are free to move, however, but they're acting on each other. So I said springs between them, but suppose these were all gravitating particles. In fact, these particles here could be Jupiter and its moons, and this external force here could be the sun. So it's a subdivision like that, it's a division of both. And we'd say the sun's so far away, it's acting on all these other guys, you know, in its way, and then they're acting on each other. If this were electromagnetism, you know, these particles could be acting on each other via their charges, but they could all be subject to an external field dial in and out.
It seems like this would get really complicated, but wait.
It would get ridiculously complicated, but there are interesting conclusions we could draw. So, yeah, anything more than 2 particles, okay, you're gonna have to bring a machine into that. Okay. But let me show you one thing we can do with this. So next, we're just gonna add all of these. Because these equations here go I equals 1 to n. So add the equations, and then the left side we have the sum over m sub I, r sub I, 2 derivatives, equals the sum over f sub I external, okay, I, plus this double sum ij, fij, I not equal to j. And what happens here, it is getting really complicated, except that this complicated expression here has an f sub ij equal to minus f sub ji for every pair that you choose. So you've got all these possibilities. Why is this? Newton's 3rd law. So we're saying all of these individuals are interacting according to Newton's 3rd law. So this double sum sums up to exactly 0. Okay. So double sum equals 0 because you take f sub ij plus f sub ji equals 0. And what that leaves you with is the sum over m sub I, r sub I second derivative equals f net external. We just add them all up and call it the net force. And we can do one other step. We'll pull out one derivative, d over dt, sum over m r I dot equals the net external force. Who sees where this is going? You guys have seen this before. If the net external force happens to be 0, the time derivative of this is 0, and the thing in parentheses is constant. What's that object in parentheses? Mass times velocity. Linear momentum, right? So the total linear momentum of the system is then conserved if you have a net external force. And yeah, this can be extremely complicated. You could have 2 giant contraptions headed for each other for a collision, they collide. There's an infinity of complicated interactions that you could never follow. And yet you know that the momentum before and after is conserved. Okay? So we'll start with this example next time. This is a really good one. Where some things remain simple even though you have a absolutely too complicated individual system. All those individual interactions here add up the zero portion of it. Good, so that's a good start into the system of point particles. What we ended up with was conservation of linear momentum. We'll start with that next time.